Bismillahirrahmanirrahim. Assalamualaikum and a very good day. In today's lesson, we are going into the final chapter of dynamics course, which is chapter 4, impulse and momentum. So today we're going to talk about the principle of linear impulse and momentum. The outcomes of today's lesson is that at the end of this class, you should be able to derive the principle of impulse and momentum. You should understand the difference between the principle of work and energy, the one that we have covered in the previous chapter, chapter 3, and the principle of impulse and momentum, which we are going to discuss today. And finally, we're going to solve a few problems using the principle of impulse and momentum. Let's recall from what we have learned in chapter 2, that is the Newton's second law of motion, which states that the total force is equal to the mass multiplied with the acceleration. So if you notice, the force is a vector written with a bold typeface, the mass is a scalar quantity, and the acceleration is also a vector. Now, this can also be written as the mass multiplied with dv over dt, because we know that the acceleration a is equal to dv over dt. So if we rearrange this equation and brings dt to the left, we have f dt equals to m dv. So to solve this, we can integrate both sides. So on the left hand side, we integrate f dt with respect to time from t1 until t2, and on the right hand side, we integrate m dv with respect to the change of velocity from v1 until v2. So what we have from this, we're gonna have the sum of f dt from t1 until t2 on the right hand side is equal to mv2 minus mv1. This is what we have from the integration. So if you notice, on the right hand side, mv is equal to the linear momentum, which is the mass multiplied with the velocity, which is also written as the capital letter L. And remember that this is a vector quantity, so L is written with a bold typeface. What is on the left hand side of the equation? The integration of f dt, or the force multiplied with time, is called linear impulse, and this is also written with a symbol, a capital letter I. And remember also that this is a vector quantity as well. So from these equations that we have derived, we can rewrite this as in this form, which we bring mv1 to the left hand side, and it becomes mv1 plus the integration of f dt is equal to mv2. So what we have here is basically initial momentum mv1, which can also be written as L1, linear momentum. Remember, I've explained before that it can be represented by the letter L. So mv1 is the initial momentum. We can write it as L1 plus the total, the integration of f dt is the total impulse, or we can write it as the total of I 1 to 2, which is the total impulse from time equals to 1 until time equals to 2. This is equal to the final momentum mv2, or we can also write it as L2. Okay, let's compare this with what we have in the previous chapter, That is the principle of work and energy. Previously, we have learned that the principle of work and energy is equal to T1, the initial kinetic energy, plus the total work done to move from position 1 until position 2, U1 to 2, is equal to T2, that is the final kinetic energy. So basically, these two principles are comparable to each other. So if you see, the principle of linear impulse and momentum states that the initial momentum plus the total impulse equals final momentum. This is similar to the principle of work and energy, which states that the initial kinetic energy plus the total work done is equal to the final kinetic energy. The difference between these two principles is that the principle of work and energy is in form of scalar equation, whereas the principle of linear impulse and momentum consists of vector quantities, and therefore it is a vector equation. Okay, so these are the difference between these two. But to avoid calculating in vector, what we can do is that we can write the principle of linear impulse and momentum into three separate axes based on the axis of the motion. So we can write it as mvx1 plus the integration of f dt equals to mvx2, and mvy1 plus the total impulse in y-axis equals to mvy2. And if we have a three-dimensional problem, then we can write it as mvz1 plus the total impulse in z-axis equals to mvz2. Okay. The same goes for if we have a system of particles. So we have learned this as well in the previous chapter where, for example, we have more than one particles acting on the same time. So what we have to do is to calculate the kinetic energy as well as the work done for every particle. So we have to do the same for this principle of linear impulse and momentum, where we have to calculate the total initial momentum plus the total impulse, and this will be equal to the total final momentum. So the principle remains the same. What the difference is only you have to calculate the momentum, the impulse, as well as the initial momentum, the impulse, and the final momentum for each and every one of the particle in the system. All right. So that is basically it for the principle of impulse and momentum. So if I go back to the principle of impulse and momentum, what we have covered is that we can write this in three separate equations based on the axis of the motion. So we can write the principle of linear impulse and momentum in x-axis, we can write it in y-axis, and if we have a three-dimensional problem, we can then write it in z-axis. All right, so let's go to the problem, example problem, so that we can see how can we implement this principle in solving the related problems. Okay, let's look at example problem 1. If the coefficient of kinetic friction between the 75 kg crate and the ground is 0.2, determine the speed of the crate when t equals to 4 seconds. the crate starts from rest and is towed by 500 Newton force. Okay, if you compare the problem in this chapter with the problems in the previous chapter, work and energy, you will notice that the difference is that in this chapter, we need to determine the speed at a particular time. Okay, whereas in the previous chapter, we are usually asked to determine the speed of the particle after it has traveled several length, for example. So this is the difference, or this is the indicator when should you use the work and energy, the principle of work and energy, and when you should use the principle of impulse and momentum. So when the problem involves displacement, what is the speed of the particle after it has displaced 5 meter, for example, then you have to use the principle of work and energy. But in this case, we need to determine the speed of the crate when t equals to 4 seconds, which means that after time equals to 4 seconds, or 4 seconds after the crate has started to move, we need to find what is the speed or the velocity. Then this is where you need to use the principle of linear impulse and momentum. So that is where the difference lies between work and energy and the impulse and momentum. So when it involves time, impulse and momentum. When it involves displacement, then you go with work and energy. All right. So first thing first is to draw the free body diagram. Okay, we have the weight pointing down, the normal force pointing up, the friction going backwards, and we can resolve the pulling force or the towing force of 500 Newton into x and y axis, 500 cos 30 in x axis and 500 sin 30 in y axis. Okay, so let's apply the principle of impulse and momentum in y axis by taking positive direction pointing upwards. And we know that it starts from rest, therefore mvy1, or the initial velocity, is equal to 0. And we also know that the crate is not moving in y-axis, therefore mvy2 is also equals to 0. Why do we have to do this? It's because we need to find what is the value of the normal axis. So we need to find the value of normal force, not normal axis. We need to find the value of normal force, which is NA. Why do we need to find NA? Because we need to find what is the value of the friction here. So friction is equal to the normal force multiplied with the coefficient of kinetic friction, mu k. So we need to find NA first. So what's left is the impulse. So impulse in this case is just basically the force multiplied with the time. So time given here is 4. So basically you look at the forces in y-axis. We have NA pointing up, which is positive. So NA, the force, multiply with time. 4 seconds, so you get the impulse. Okay, and you have also 500 sine 30 pointing up, positive, so plus 500 sine 30, the force, multiply with time 4, then you have the impulse. And then we have the weight pointing down, so minus 75 times 9.81, that is the force, the weight, multiply with time 4 seconds, then you have the impulse. So this is how you calculate the impulse. And by solving this, you will get NA equals to 485.8 Newton. Okay, once we have the normal force, we can go ahead and calculate the friction force, which is NA multiplied with mu k, that is equals to 0.2. So you will have the friction force equals 97.15 Newton. Once we have this, we can go ahead and use the principle of impulse and momentum in x-axis. This is the one that we are interested in because obviously the motion of the crate is in x-axis. And we know that it starts from rest, therefore mvx1 is equal to 0. What's left is the impulse in x-axis, and then the velocity, the vx2, which is the speed that we are going to find out. So the impulse in x-axis, it is pretty much similar to calculating the impulse in y-axis. You'll be looking at the forces acting in x-axis. So what you have is the positive component of towing force, 500 cos 30, the force, multiplied with the time 4, you have the impulse. And then you have the friction force pointing backwards, which is negative, and you multiply 97.15 with 4, then you have the impulse. On the right hand side, it's the mass times Vx2, which is 75 times Vx2. So solving the equation, finally we get the velocity. We get the velocity of the crate after t equals to 4 seconds, or at t equals to 4 seconds, is equal to 17.91 meter per second. Okay, let's look at the next example. The motor exerts a force of F equals to 20 T square Newton on the cable. Okay, the difference between this problem and the previous problem is that the previous problem we have a constant towing force. In this problem we have a variable force exerted by the motor, and it varies with time. F equals to 20 times T square. So as the time increases, the force also increases. All right. Determine the speed of the 25 kg crate when t equals to 4 seconds. Again, you see the time is mentioned here, so you know that you have to use the principle of linear impulse and momentum. The coefficient of static and kinetic friction between the crate and the plane are mu s equals to 0.3, mu k equals to 0.25. Okay, this is another trick question. When you see both coefficient of static and kinetic frictions given, then you need to determine when the crate or the box starts to move. Okay, that is the question first before you start calculating. Let's draw the free body diagram first. Okay, the crate will have the weight pointing down, normal force pointing up, the friction pointing backwards, and the towing force by the motor F equals to 20 T square. Like I mentioned earlier, when does the crate starts moving? If it is if only the kinetic coefficient, or the coefficient of kinetic friction is given, like the one we had in the first example, then we know that the crate moves straight away. But when both static and kinetic friction coefficients are given, then you need to know what is the time when the crate starts to move. Do you know what is the time it starts to move? It starts moving when the force exerted by the motor exceeds the normal force multiplied with the coefficient of static friction. That is when the box cannot hold, the static friction cannot hold the crate anymore because of the forces applied, because of the force applied by the motor, and therefore it is going to move. So this is what we need to determine first. That is, when does the crate starts moving? So how to do this? We're going to use what we have learned in chapter 2, solving the forces in y-axis. And we know that the crate doesn't move in y-axis, so sum of force Fy equals to 0. So we're going to have Na equals to mg, that is equal to 245.25 Newton. From this, we can then calculate the time which the box starts to move. So if we calculate the forces in x-axis, we have 20t square positive minus 245.25, that is the Na multiplied with the coefficient of static friction, which is 0.3, equals to 0, because as the force is equal to the friction, it only about to move, it hasn't moved yet, so this is the acceleration is still equals to 0. So this is the logic behind this calculation. So from this you can determine what is the time at which the crate starts to move. So solving the equation, we know that the crate starts moving at t equals to 1.918 seconds. All right, when you have this information, then only we can proceed with the principle of impulse and momentum in x-axis, because this is obviously what we are interested in, to know what is the speed of the crate at time t equals to 4. So basically we have, we know that it starts from not moving. Okay, the force is being applied to the crate, and because of the static friction, it is not moving yet until a certain time, until time t equals to 1.918 seconds, then only it starts to move. So therefore mvx1 is equal to 0. So initial velocity is equal to 0. Then the impulse is, it is no longer integration from 0 to 4, because we want to know what is the impulse during which the motion occurs. So the motion occurs from t equals to 1.918 until 4. So that will be the range of the integration. So integration from 1.918 until 4 fx dt equals to mvx2. All right, so the integration of fx dt, if you look at the x-axis, we have two forces. The first one is the friction, the second one is the force F equals to 20t square. Let's look at the friction first. The friction is now the normal force, which is 245.25 multiplied with the coefficient of kinetic friction, mu k, is because the crate is already moving. So we are no longer using static friction, but we use the kinetic friction. And because of the integration, and because we integrate not from 0 to 4, but from 1.9 to 4, so what we need to do is we have to multiply 245.25 multiply with 0.25, the kinetic friction. You will have the friction force. The time is 4, so multiply with the time, you get the impulse. This is for the top range. The bottom range, you still have to include, which is you have to minus 245.25 times 0.25 times 1.918. This is the integration. So previously we don't have to do this because it is multiplied with 0, because our lower range is 0 to 4 in the example number 1. But in this case, it is from 1.918 to 4, so we have to do this. And remember that the friction is in the negative direction, therefore in front here you have to write negative. Okay, that is for the FR. And we also need to do the integration of the variable force, integrate from 1.9 until 4 20t square dt, which is equal to 25 vx2. Vx2 is the one that we are interested in finding. So for the integration of 20t square dt, what you will get is 20t to the power of 3 divided by 3. And since we have the range, we have to substitute the value. So 20 times 4 cube divided by 3 minus 20 times 1.918 to the power of 3 divided by 3. That is equal to 25 vx2. And solving the equation, you will have vx2 is equal to 10.08 meter per second. Okay. Now let's look at the final example. The 10 kg block A attains a velocity of 1 meter per second in 5 seconds starting from rest. Determine the tension in the cord and the coefficient of kinetic friction between block A and the horizontal plane. Neglect the weight of the pulley. Block B has a mass of 8 kg. Okay, this is a little bit differently asked, but it is still the same. It involves time equals to 5 seconds. The speed or the velocity is given, but now we need to find what is the tension and what is the coefficient of kinetic friction. So we need to do this block by block. So first thing first, draw the free body diagram. For block B, down here we have the tension and the weight only. For block A, we have 4 external forces acting on it. We have the weight, we have the normal reaction force, we have the friction as well as the tension. So let's go to block B first so that we can find the tension. We use the principle of impulse and momentum in y-axis, taking downwards as positive because that is the motion of the block. So we know that it starts from rest, therefore mv1 equals to 0. The integration of Fy dt is from 0 to 5. We don't have to find the time when the block starts to move because the coefficient of static friction is not given. So we know that this thing moves immediately after it was released. So mv2, v2 is given. V2 here is 1 meter per second. So what we have is then 8 times 9.81, the weight, multiply with 5 to get the impulse, minus the tension in the opposite direction, multiply with 5, you get the impulse for the tension, equals to 8 the mass times 1 is the velocity. So we get the tension equals to 76.88 Newton. Once we have the tension, we can go to block A, but first we need to find what is the value of the reaction force so that we can calculate the friction force. So by using Fy equals to 0, we get Na equals to 98.1. This is basically Na equals to the weight. And then we can go ahead with the principle of impulse and momentum in x-axis. Okay, starts from rest, so mv1 equals to 0. Integration of fx dt from 0 to 5 equals to mv2. V2 is the one that we want to find out. Okay, and then we have 76.88. This is the tension. Multiply with 5, it becomes the impulse, minus the friction. 98.1 is the normal force. To make it a friction, we have to multiply with mu k. This is the one that we want to find. What is the value of mu k? Multiply with 5 seconds to make it the impulse, equals to m 10 kg for block A. 1 is the velocity. So solving this equation, we finally get mu k equals to 0.7633. All right. So in summary, what we have learned in this video is we have learned about the derivation of the principle of impulse and momentum. Basically, it comes from the Newton's second law of motion, F equals to ma. Then you do some rewriting of the equation and rearranging it. And finally, with some integration, you will get the principle of impulse and momentum. And you have seen what is the difference between the principle of impulse and momentum and the principle of work and energy. Basically, work and energy you use when the problem involves displacement. The principle of impulse and momentum is going to be used when the problem involves time. And finally, we have seen 3 related problems solved using the principle of impulse and momentum. Alright, so that's all for this video, and I hope to see you in the next video. Thank you.